Neodymium was discovered in 1885 by an Australian chemist named Carl Ove von Wellbach. At first, scientists believed it was part of a single element called didymium. However, through spectral analysis, Carl Ove von Wellbach proved that didymium was actually a mixture of two elements, which are neodymium, meaning new didymium, and praseodymium, known as green didymium. The name neodymium comes from the Greek word neos, meaning new, and didymos, meaning twin. This name reflects its discovery as one of the twin elements separated from didymium.
Neodymium has the chemical symbol Nd and an atomic number of 60, placing it in period 6 of the periodic table. It is hard, slightly malleable, silvery metal that tarnishes quickly when exposed to air and moisture. Neodymium is considered a toxic heavy metal and has a relatively high melting point of 1021 degrees Celsius, which is typical for metals with strong metallic bonding.
Most of us, with things like earphones,
helium, then lithium, beryllium, boron, carbon everywhere, nitrogen all through the air, with oxygen so you can breathe, and fluorine for your breathing.
laptops, or electric motors every single day. But we rarely stop and ask, how does this material actually works? One metal that quietly powers a lot of modern technology is neodymium. It is used in some of the strongest magnets in the world, such as speakers, hard drives, and electric vehicles. The objective of this presentation is, first, to explain the concept of metallic bonding, second, to describe band theory in metals, and finally, to apply these theories and understand the properties and application of neodymium metal. So in this video, we'll break down these two concepts step by step, and then connect them directly to neodymium as a real-life useful metal. Let's start with the foundation of metallic bonding. Why is my phone charging so slowly? I just changed the cables.
Cheap cables usually use poor quality metal conductors.
So it's actually a chemistry problem?
Exactly, and that's where metallic bonding comes in. When we think about bonding, we often imagine atoms sharing or transferring electrons, like in covalent or ionic bonds. But metals work differently. In metallic bonding, metal atoms release their valence electrons, forming a structure of positive metal ions surrounded by a sea of delocalized electrons. These electrons do not belong to any one atom. They move freely throughout the entire metal structure, and that movement is the key to many metallic properties. For example, when electricity flows through a metal wire, it is these free electrons that carry the charge. Metallic bonding also explains why metals are malleable and ductile. When force is applied, the metal ions can shift position without breaking the bond, because the electrons are shared collectively rather than between fixed pairs of atoms. So, metallic bonding explains the structure and basic physical properties of metals, but it doesn't fully explain how electrons behave at different energy levels. I get that electrons are free, but how do they know where to go?
They don't know. It's about energy level.
Energy levels? Like bands?
Exactly. That's band theory. Band theory helps us to understand what happens to electrons when a huge number of atoms come together to form a solid. Instead of having separated atomic orbital, the orbital overlap is split into continuous range of energy called bands. The two most important ones are the valence band, where electron normally exist, and the conduction band, where electron can move freely through the material. In metal, these two bands overlap. This means electron can move into conductive state with almost no energy input. That's why metal conduct electricity so easily, even at low temperature. In comparison, insulators have a large energy gap between these bands, while semiconductors have a small gap that needs some energy to cross. Band theory doesn't replace metallic bonding. It completes the picture by explaining the electronic behavior of metal at atomic level.
Wait, why is this magnet so strong?
That's neodymium.
Oh, this is the kind that is used in headphones and phones, right?
Exactly, and this property makes sense once you understand metallic bonding and band theory. Neodymium is a rare earth metal with the electronic configuration xenon 4F46s2, and the configuration is key to its properties. Like other metals, neodymium forms strong metallic bonds, allowing electrons to move freely and giving it typical metallic properties such as conductivity and strength. According to band theory, neodymium has overlapping energy bands, which further supports its ability to conduct electric efficiently. What really sets neodymium apart is its unpaired 4F electrons. These electrons create strong magnetic moments. When neodymium is combined with iron and boron, it forms ND-FeB magnets, the strongest permanent magnets currently available. That's why neodymium is used in compact but powerful devices like headphones, wind turbine, computer hard drives, and electric vehicle motors. In short, neodymium isn't just interesting on paper, it's essential in modern technology.
So, when we put everything together, metallic bonding explains how metal atoms stay connected through delocalized electrons, giving metals their strength and flexibility. Band theory explains how these electrons occupy energy bands, allowing metals to conduct electricity efficiently. By applying these concepts to neodymium, we can understand why it has both strong metallic and magnetic properties, making it valuable in modern devices. However, the growing demand for neodymium also raises environmental and sustainability concerns, especially in mining and resource management, which highlights the importance of responsible material use. This shows how chemistry is not only about theory but also about real-world impact and responsibility.
All information used in this presentation was obtained from credible academic sources and is properly references. Thank you for watching. Don't forget to like and comment.
First, to explain the concept of metallic bending.
Bonding!
When we think about metal,
However, the growing demand for neodymium also raises concerns. Tak ada concern?
But it's essential in modern technology.
In comparison, insulators have a large energy gap between its bands, while semiconductor greater lah.
Why is this magnet so strong?
That's neodymium.
Oh, it's the kind that is used in headphones and phones, right?
Exactly, and its property makes sense once you understand metallic bonding and its band theory.
when we think about metallic bonding, we often imagine atoms sharing.
Everything together, metallic bonding explains how metal atoms stay connected through Apa benda ni? 1